Welcome again. Let's continue new chapter 12, and this is lecture number 7. Chapter 12 is about the thermodynamic property relations. First of all, let's try to discuss the objective of this chapter. Mainly, this chapter is quite different than the previous chapter because most of the time mathematics will be involved in this chapter, and the first major objective of this chapter is we have two types of the property. One is the directly measurable property, like temperature, pressure, volume. We can measure it with the help of certain instrument, so we call that directly measurable property. But the other property which are not directly measurable, for example enthalpy, internal energy, entropy, these are the indirectly measurable property. So we should have certain mathematical relationship between the directly measurable property and indirectly measurable property. So the first objective of this chapter will be to develop fundamental relations between the commonly encountered thermodynamic property and express the property that cannot be measured directly, right? So in terms of easily measurable property. So that would be the first objective. And then there is a very famous relationship that's called Maxwell relations. Maxwell relations is basically a set of partial differential equations that are very important in thermodynamics because those are the fundamental for driving another thermodynamic property. So we'll try to develop a relations for Maxwell in this chapter, and then we'll try to develop Clapyron equation from the Maxwell equation. Clapyron equation is again a very famous equation. That's the equation of enthalpy of vaporization. That means we can calculate the enthalpy of vaporization if we know the value of pressure, volume and temperature, which are the directly measurable property. So from the directly measurable property, if we have a mathematical relation, we can measure enthalpy of vaporization. And then we'll try to develop the relationship between CV, CP, you know that du, dH and ds for all pure substances. And then we'll discuss Joule-Thomson coefficient. And lastly, up till now you have derived relationship for enthalpy change, internal energy change and entropy change for real gases. But in this chapter we'll try to develop these relations for real gases. So that would be quite different than your previous chapters, right? So these are the major objectives. So you can see as a whole a lot of mathematics will involve in this chapter. So let's start with the fundamental. We call the derivative, partial derivative and total derivative. Now let's see first of all the simple derivative. We know that we can express any state of a substance if we know two independent intensive properties. Now the role of the derivative is, let's say we have a function f, and that function f is a function of x, right? So that means f is varying with respect to x. You can see let's say this is the initial one, and then after certain change in position, let's say delta x, the new value of the function is f x plus delta x. Now what the derivative basically indicates? Derivative, you already know that this is a kind of approximation. For example, now this function f is varying in this direction. Now if we assume that delta x is very small, let's say this delta x is very small, then the slope of this straight line will be equal to the derivative, and that will represent the rate of change, right, of x with respect to x. So that's basically the fundamental meaning of the derivative, that the derivative is an approximation. For example, this is a curve, and if we split that curve into small parts, let's say this one, let's say this is delta x, again let's say this is delta x. Now the slope of this will be equal to derivative, and that will represent the rate of change of x with respect to x. So that's called the simple derivative. And then to see the application of the simple derivative in thermodynamics, we can take this example. For example, the Cp of an ideal gas depends on temperature only, and mathematically that Cp is a function of temperature, and that's equal to the derivative of enthalpy with respect to temperature. So let's say determine the value of Cp of air at 300 Kelvin using the enthalpy data from table, let's say A17, and then compare, because the value determined from the derivative, that will be approximation, and then compare that approximation with the exact value that is available in table A to B, right? So that means that relationship, basically, let's say what that derivative indicate, that this is basically H, that's H, and on horizontal we have temperature, right, that temperature, and there is the function H is varying with the temperature. Now if we take any points, let's say point, we need to calculate which temperature, at temperature of 300 Kelvin. So let's say this is our 300 Kelvin temperature at this point, let's say this one, right? So that means if we take the slope of that, let's say for a very small interval, if we take very small interval, then the slope of this should be equal to Cp. So that's how the derivative is involved. So that means the point at which we want to calculate the value, let's say 300, if we take very nearest point, any nearest point, let's say that's 300, the nearest point could be 295, similarly the nearest point could be 305. So if we take a very small delta t, and at that small delta t, if we take the slope, then that slope will be equal to the derivative, and that derivative is basically the value of the Cp. So let's try to do that. For example, from table A17 we can read the value of the enthalpy. Let's say this is the point where we need to calculate at 300, we need to calculate the value of the Cp. So we know that from that table the value of the enthalpy is 300.919, and then the nearest point is 295 Kelvin and 305 Kelvin. So again at those points 305 we have enthalpy value, again we have enthalpy value. Let's try to take first the point 300 and 305. I mean this is the 300 points, this one, let's say, and the next point is 305. Let's say this is 305. So now if we take the derivative of this, then Cp value by using the 2, that's the delta H divided by delta T. So delta T is 5, the value of Cp is 1.006 kilo, all units are in SI, kilojoule per kg per Kelvin. And similarly we can take another 2 points. Let's say instead of taking 300 and 305, we can also take these 2 points, 295 and 300, and if we again apply that, then the Cp value, that's the delta H divided by delta T, so that value is 1.004. We can also take 295 and 305, so that's the third option. Let's say 305 and 295, if we again put the values, then we'll get the value of the Cp equal to 1.005. so you can see that if the delta T is very small, in all the 3 cases the delta T value is 5, right? So if the delta T value is very small, you can see the value of Cp is almost equal. There is a difference of although 0.001, but that difference is negligible. Now if we try to read the value, exact value from that table A to B, then the value of Cp is 1.005 kilojoule per kg per Kelvin. So that indicate that the derivative give you an approximation value. All the 3 values are close to the exact value, provided that the value of that delta T is very small. So that's basically the limitation of the derivative, that for any kind of function at any point you can approximate the value provided the delta T is very small, right? So this was the simple derivative. Then we also have the partial differentials or partial derivative. Sometimes any function can be a function of 2 independent variables, let's say x and y. So in that case, if the z value z value is varying with respect to x but y is constant, then we call the partial derivative of x with respect to x. So we can represent that this symbol is for the partial derivative, that means partial derivative of z with respect to x when y is a constant. And you can see this is the initial value when the value of z is x, y, and what is changing out of this? The changing is x plus delta x. So basically x plus delta x is changing, whereas y value is the same. So we can say that's the partial derivative of z with respect to x when y is a constant. Again, the limit is delta x should be very small, or it should be approaching to 0. So that's how we call the partial derivative, and this is the graphical representation of the partial derivative. You can see that z value, that z function is not varying along the y-axis. It's not varying, it is held constant. It is only varying along the z-axis. So that's why partial derivative of z with respect to x when y is kept constant. So that's called the partial differential or partial derivative, right? That symbol, this symbol that represent for the partial derivative, where the simple d that represent for the total derivative. Now let's try to see the total derivative. We have three types of the differential. One is called simple differential, partial differential, and now the total differential. Now total differential mean when that function z is varying both along the x-axis as well as along the y-axis. These are the two independent variables. When that function z is varying with respect to x as well as with respect to y, then we called total differential. And how can we derive the relation for the total differential? Now let's say that's delta z. This is the initial value of z x with respect to x and y, and you can see the change in x as well as change in y. So x plus delta x comma y plus delta y. Now if we add and subtract this value, right, in the above equation, let's say this is the subtraction and this is the addition, right? This is the in the above equation, and then we divide this portion with delta x and multiply with the same value, right? Similarly, we divide with the delta y and multiply with the same value. Then, and if we take limit for this one, if we take limit delta x approaching to 0, and for this one, if we take delta y approaching to 0, then what is the value of this term and what is the value of this term? You can see that now here what is changing. If you look carefully, the initial value is x comma y plus delta y, and what is changing here? X plus delta x, whereas y plus delta y is here. Similarly, y plus delta y is here. So that means we can write this term as partial derivative of z with respect to x when y is constant into delta x. Similarly, what is changing in this term? Now here we have x comma y, and now x is constant, y plus delta y is changing. So what is this term? That's partial derivative of z with respect to y when x is held constant. So we can write the above equation. This term is basically partial derivative of z with respect to x when y is constant into dx plus partial derivative of z with respect to y when x is constant into dy. So this is called total differential. Now you can see total differential means that variable x and that variable z as a function of x and y is varying both with x as well as with y. So that's called this. The first term is represented with delta x, the second term represented with delta y. So that's called total differential. To understand the total differential, you should do some practice as well. Let's assume that enthalpy of a real gas is a function of pressure and temperature. So what will be the total differential of enthalpy? If the enthalpy is varying with pressure and temperature, then the delta H, that means the total differential of enthalpy, that's equal to partial H by partial P first when T is constant into delta P plus partial H divided by partial T when P is constant into delta T. So you can see, that's varying both with pressure as well as with the temperature. The first term is partial H by partial P when T is constant into delta P plus partial H by partial T when P is constant into delta T. So that's how the differential is involved. Now let's see another example. Let's say the volume of the real gas is varying or is a function of pressure and temperature. Then what's the differential of the volume now? The differential of the volume will be the total differential is equal to partial derivative of V with respect to P when T is constant into delta P plus partial derivative of V with respect to temperature when P is constant into delta T. So this is this second example. Please try to practice the total differential, how you can write if any function is varying with more than one variable. So that's called the total differential. Now you can see basically we have three types of the differential. One we call the simple differential, then we have the partial differential, then we have the total derivative or total differential. Now let's have some practice for the total differential. Now consider air is at 300 Kelvin and 0.86 cubic meter per kg. The state of the air changes to 302 Kelvin and 0.87 cubic meter per kg as a result of some disturbance. So as a result of some disturbance, the state of the air is changed. This is the initial state. So from initial state, the state is changed to the new state, right? So this is the new state as a result of some disturbance. So use that equation. That equation is basically the equation for the total differential. So use the total differential and estimate the change in the pressure of the air. So how the pressure is changing as a result of this disturbance, right? Now let's say that air is an ideal gas, and in this equation we are given that we have this state 1, right, and this is state 2. So the state 2 is as a result of some disturbance. So what is happening with the pressure? We are given that the delta T is equal to 2 Kelvin and a change in volume is, specific volume is 0.01 cubic meter per kg. We need to figure out what is the change in the pressure as a result of this disturbance. Now we know we can treat air as an ideal gas, and the ideal gas equation is PV is equal to RT. We are not considering here mass because we are using per kg, I mean the specific volume. So the pressure will be RT by V. So you can see R is a constant. So pressure is a function of temperature and specific volume. So pressure is a function of specific volume and temperature. Now what will be the total differential of pressure now? What is the total differential of pressure now? So delta P will be equal to partial P by partial V when T is constant into delta V plus partial P by partial T when V is constant into delta T. So that would be the total differential of the pressure when it is a function of specific volume and temperature. Now we need these two terms, the first term and the second term, and then we can evaluate the change in pressure. So let's try to calculate the first term first, this one. This term is basically partial P by partial V when temperature is constant. So that means we have to take the partial derivative of pressure with respect to specific volume, and we have to take temperature constant. So in that equation, if we take R is already constant, we have to take the temperature as well constant. So only variable is V, right, with respect to V. So what will be the value? The value will be RT over minus 1 by V square. So we'll get this one, minus RT by V square, and this will be as it is. So this is the first term. So how to evaluate the second term? Again, for the second term we have to take the derivative of the pressure with respect to temperature. Now we have to take specific volume constant. So if we take this one, so temperature, right, this is constant, this is constant. So if we take with respect to temperature, we'll get R by V. So we'll get R by V, and delta T is as it is. So if we put these two values in this equation, then we'll get delta P is equal to minus RT by V square into delta V plus R by V into delta V. Now if we simplify, r will be constant, then inside we'll have delta T by V minus T by V square into delta V. Now we have all the values. We know the value of r for the air is 0.287. We know the delta T is here 2 Kelvin, and then we have the volume specific. We can take the average specific volume. Similarly, the temperature, average temperature. Now we have the delta V, that's the delta V, and then we have V square. We can take average specific volume. So if we simplify, we'll get the change in pressure as a minus 0.491 kilopascal. The negative sign indicates that there is a decrease in pressure, right? So this is how, that means the pressure is decreasing. So that means if air is at this state, right, this is the initial state, that's the initial state. So if the state of the air is changing from 1 to 2 as a result of some disturbance, then the pressure will be decreasing of this value 0.491 kilopascal. So that's the application of the total differential, that we can by changing some variable we can see the impact on another variable. This is how the total derivative is applying. Let's see another example. Let's say the radius and height of a cylinder are both 2 centimeters. So there is a cylinder which have radius and height equal, and that value is 2 centimeter. The radius is decreased at 1 centimeter per second. So in one second the radius is decreasing at this rate, whereas height is increasing at 2 centimeter per second. What is the change in volume with respect to time at this instant? So we need to figure out, as a result of the decrease in radius and increase in height, what is the impact on volume. So again we know that the volume of the cylinder is equal to pi r square h. Now you can see volume, we are given that the radius is decreasing at a rate 1 centimeter per second. Negative sign indicates that it is decreasing. Similarly, the height is increasing at a rate 2 centimeter per second. Now you can see volume is basically a function of radius and height. So can we take the total derivative of volume? Yes, the total derivative of the volume is equal to partial V by partial R when H is constant into dr plus partial V by partial H when R is constant into delta H. Now we need to calculate these two terms. The first term is we have to take the derivative of volume with respect to R when H is constant, and then we have to take the derivative of volume with respect to H when R is constant. So let's try to calculate the first. We need to calculate on the basis of time, so we have to divide both sides with the time. So if we divide this with the time, then we need to divide delta T, we need to divide with the delta T. Now we need to calculate this term now first. So this term is basically derivative of volume with respect to R. So if we take the derivative of volume with respect to R, that will be pi 2R into H. So 2 pi R H, and this term will be as it is. So what will be the value of this derivative of volume with respect to H, and R is constant. So derivative of volume, that means pi r square. So we'll get pi r square. So this term will be as it is. Now if we put all the values, 2 pi, we put value of r, value of h, value of -1, then pi r square, and then the value of this, then we'll get 0. So that's very interesting. That indicates that the volume of this cylinder is not changing. That means that delta V by delta T is equal to 0. So although the radius is decreasing at a rate of -1 centimeter per second and height is increasing at a rate of 2 centimeter per second, but the change in volume is 0. So that's very interesting. So this is another application of the total derivative. Now let's extend this. let's extend this concept. So first of all, we study the partial derivative, that if z is a function of x and y, we can write down the total differential of z. I mean, if z is a function of x and y, right, x and y, and then we can write down this total differential. Let's say that this dz is equal to m dx plus n dy. That means this value is now m dx plus n dy. So that means we can write down that the first term, let's say, that's m, second term is, let's say, n. Now if we take further derivative of m, I mean, let's say this is already derivative with respect to x. Let's say if we take the second derivative, let's say partial m by partial y, now x is constant, then we'll get the second derivative, partial square z by partial y. Now so partial x is as it is because x is constant. So similarly, if we take partial n by partial x when y is constant, so y is constant, so it is as it is, so partial square z by partial x. Now you can see the both values, this one and this one, they are the same. Why they are the same? I mean, the order of the differentiation is immaterial for the properties, because properties, they are the continuous point function. I mean, properties, they depends on the end points, they don't depend on the path, so that's why they have the exact differential. So we can say, since this value is equal to this value, so both, this is partial m by partial y when x is constant, that's equal to partial n by partial x when y is constant. This is very important relationship that will be used in the driving the Maxwell relation and also driving many other thermodynamic property relation. That means the second derivative of any variable, that's the equal, but the condition is if they are the continuous point function, right? So let's extend this further. I mean that z, when the z is a function of x and y, then we can write down the total differential as it is. Let's say if we have x as a function of, let's say, y and z, then what will be the differential of x? Differential of x will be dx is equal to partial x by partial y when z is constant into dy plus partial x by partial z, y is constant, into dz. Now let's try to, because I mean, integrate these two. How can we integrate these two? I mean, we can put this x in that equation here. In other words, we can, by eliminating dx. So if we put this dx in that equation, then we'll get, by rearranging, I mean by combining the delta y term and the delta z term, and again we have here delta z term and delta z term, they will come on the one side, right? So further we can simplify, I mean rearranging, delta y term is on one side, whereas delta z term is on one side, similarly delta y term is on another side. Now these two, we have independent variable, delta y is also independent variable, delta z is also independent variable. So when the two independent variable, then this equation is valid only when this term is also equal to 0 as well as this term is also equal to 0, then two independent variable can be equal. So that means if we put the first term equal to 0, let's say this one equal to 0, then 1 will be on one side and this 2 will be go on the other side. In other words, partial x by partial z when y is equal to constant is equal to 1 by partial z by partial x when y is equal to constant. So that's called reciprocity relation. I mean, you can see this is the same one. You can see partial x by partial z is equal to 1 by partial z by partial x. So basically that's the reciprocity. I mean x by z, z by x. So both that's available at y comp. That's called the reciprocity relation. Again, if we simplify the left hand side, then I mean that left hand side, let's say this plus sign that goes to the right side, then it will be minus partial x by partial y. So if we divide both sides with this one, we'll get minus 1 and we'll get this one. So that's called partial x by partial y by partial z by partial x. That's equal to minus 1. That relationship is called cyclic relations. Cyclic relations mean, let's say we have 3 variable. That's for the 3, let's say pressure, volume, let's say temperature. Let's say 3 variable. So how can we write down, the cyclic relation for this one? By using this one. Let's say this is x, y, z. So we can write down, how can we relate these 3 independent variable? Like partial p by partial y when v is constant, partial v by partial t when p is equal to constant, partial z by partial p when v is constant. That should be equal to 1. So that means if we have 3 independent variable, which is x, y, and z, so how can we relate those 3 independent variable? We can relate those independent variable by using cyclic relation. So partial x by partial y when z is constant, partial y by partial z when x is constant, partial z by partial x when y is equal to constant is equal to minus 1. Please try to practice these 2 relations, reciprocity relations and cyclic relations. Now let's try to do one example so that we can understand the verification. We can verify that theoretical concept of cyclic and reciprocity relation. Let's try to apply that relations on ideal gas equation. So the question is, using the ideal gas equation of state, verify the cyclic relation and reciprocity relation at constant pressure. So let's try to do the first one. We know that the ideal gas equation is PV is equal to RT. So what will be the cyclic relation? Cyclic relation mean there should be 3 variable. Let's say pressure, volume, and temperature. Pressure, volume, and temperature. So how can we write down the cyclic relation for this one? We can write down, like, let's say starting from the pressure. Let's say partial P by partial V when T is constant, then partial V by partial T when P is equal to constant, then partial T by partial P when V is equal to constant. So that should be equal to minus 1. So if we try to calculate these three terms for the ideal gas, then the product of these 3 terms should be equal to minus 1. So let's try to calculate the first term. Let's say the first term is partial P by partial V when temperature is equal to constant. So please take that derivative of pressure with respect to volume. So that value will be equal to minus RT by V square. What about the second term? The second term is partial V by partial T at constant pressure. So again take the derivative of now the volume with respect to temperature. Now keep pressure constant. So that value will be R by P. Now let's try to take the third term now. The third term is partial T by partial P when V is constant. So if we take that from this one, what will be the value? Now we have to keep the volume constant now, right? And we have to take the derivative of temperature now. So derivative of the temperature with respect to pressure, that will be V by R, right? So now we have the 3 terms. If we put these 3 terms in that equation, right, if we put that, let's say this is the first term, minus RT by V square, this is the second term, and then the third term. So if we multiply, we'll get minus RT by PV. Whereas what is the value of RT by PV? From this equation, what is the value of RT? So if PV comes in this side, so here we'll have 1 only, so that means minus 1. So that indicates that the product of the 3 value is equal to minus 1. So that was the verification of cyclic relation. What about the verification of the reciprocity relation at constant pressure? So that means at constant pressure we have to verify. So at constant pressure, so that means, let's say partial derivative of V with respect to temperature, that should be equal to 1 by partial T by partial V at constant pressure. So then we need to calculate these 2 terms. If they are equal, then we can verify. So this term partial V by partial T at constant pressure is equal to RP. That means we have to take the derivative of specific volume with respect to temperature at constant P. So that value is R by P. Similarly, 1 by, now we have to take the derivative of temperature with respect to V when P is constant. So that's equal to 1 by P by R. So that's value is R by P. So both values are equal. So hence verified the reciprocity relations. So that's the end of this lecture. I hope you understand. If you have any question, you can ask me on the team or you can email me. See you in the next class.